So, my name is Doug. I'm going to talk about vector search. And vector search algorithms are kind of like my Pokemon. I try to collect them all. There's a lot of them, and this is a thing that's been around for a while, and it's an interesting field. And it lets me bring out the dormant C programmer in me that has been laying dormant for about 10 years, so that's exciting. And yeah, just a bit about me. Everything I should have, disclaimer, none of these opinions are Reddit's opinions, except for the ones you don't like. Yeah, just a bit about me. I think people generally know me, but Software Doug everywhere, Software Doug on LinkedIn. I move this annoying thing. Try to get that out of the way. So look for me. I'm Dougie and a Snuggie everywhere. Except on LinkedIn, I'm a little more professional, but who knows? Maybe I'll switch back. So some of the stuff I've worked on. So yeah, feel free to connect. I'm a pretty online person, for better or for worse, and so I'm happy to talk with you on LinkedIn. And one thing I will plug, I don't have a link here, the Search Relevance Slack community has a jobs board, and that is a great place to go look for. I know there's just a lot of churn, layoffs, return to office, all that stuff. Definitely check that out. It's pretty well maintained. A couple of people like David Albrecht have helped to maintain there's actually a job search site there. And second, we are actually hiring at Reddit. I believe we're hiring for a search infrastructure person and a director of product. Is that right, John? Am I missing any?
I think that's it, and there's more coming, I think.
And more coming, yeah. I'm not used to these Meetup things that apparently are from the before times, so I have to remember all these plugs. So, I'm going to talk a bit about, today we're going to talk about vector search the hard way, and like I said, I like to collect vector search algorithms, talk about a couple of them, and that's why I call it the hard way, because there's actually, I think there's more trade-offs than we actually take into consideration. Sort of my straw man argument, how many people know what ANN benchmarks is? A couple people. So ANN benchmarks is this place you go, and you can see over here on the right a bunch of different algorithms and implementations of vector search. And basically you can see HNSW is a very common algorithm these days. And then you have things like Lucine's algorithm in here. Annoy is kind of a classic one from 2015 that maybe you could say is something that kind of kicked off vector retrieval. And there's all kinds of stuff in here, and you can click them on and explore them for different data sets to see how they perform. And the important thing to look at in this graph is this recall x-axis that is like basically, did I get all the things I would expect to get? And then queries per second. And that's a logarithmic scale. So you have like 10,000, 1,000, 100. And you can see this as we play with the parameters to get all the stuff we want, the performance tanks, and that's the knob we have to play with, right? A lot of what we've done in vector search up to this point has been very much focused, I would say, on scientific benchmarking or the benchmarking regime. And benchmarks are useful, but they can kind of make you extremely hyper-focused on one thing, which is I build something, I search, it's either fast, that thing I built never changes, it's never updated, I could just search it a lot and see how good the performance is. And that's what you'll find. And I think, honestly, it would be interesting to come up with other kinds of benchmarks, like can we get recall relative to a certain update volume or something. So of course, real life systems, we all know if we're working search, there are constant updates, constant deletes, there's just churn. Lucene indices and other things are just constantly being merged together and thrown apart. There's searches happening while that's happening. We only have so much RAM, we can't fit every vector we find into memory, right? And we are sharded, and we're not only sharded in terms of actual nodes, we are sharded in terms of the things like segments in Lucene, which are the physical manifestations of the index that periodically have to be merged together. And they're searched in parallel. So, and these realities exist because we have these have to serve other applications besides just vector retrieval, including constantly updating things and regular search, filtering, analytics, faceting, all kinds of things that we need and I'm thinking mostly about a traditional search solution, but I think that also applies in other contexts as well. So this is kind of the benchmark regime on the top, trying to get high recall for low latency, and then real life is at the bottom. Updates need to happen constantly. We can't just absorb RAM, all that stuff. And unfortunately, the in real life stuff complicates our lives. But it also gives us jobs, so we can't complain too much. So I'm going to start at the end. I'm going to talk to you a little bit about, at a kind of high level, what HNSW is. So HNSW is maybe, I don't know if you might say the gold standard algorithm of vector retrieval. It's what Lucene has internally. It's what a lot of people work with. And not just HNSW, but this idea of graphs as a means to get nearest neighbors. So when I say vector retrieval, when I say nearest neighbors, you can think about those as interchangeable. It's like, I want to find the vector that is closest to me, which might be the closest in some distance measure. If I have like 100 items in a row and another 100 items in a row, what are the closest things by some distance measure? And there's a bunch of different distance measures that we could talk about. But the main thing is when we focus on just these kinds of metrics, these incentives, we are sort of, what we would like to do is basically, if you think about how would I cheat at this, I would pre-compute the right answer, and I would make sure that I had that in my back pocket to always give someone. And I don't, cheating, it's not really cheating if that's really our incentives. And that's really what graphs do. And so, and just really quick, and I'll do some live slide editing, just to kind of get at what I mean by this. When we're talking about nearest neighbors, of course, we think about like X, Y, Z. That's 3 dimensions, right? With vectors, we have like maybe a few hundred dimensions. So we have A0 through I don't know, B20 or something. And when I'm saying like nearest neighbors, often what we want is like X is 0.1, Y is 0.5, Z is negative 0.2. And we might say that like this thing I'm about to type is really far, right? This is not one of the nearest neighbors. But when we think about like something like this might be, let's say, in a question answering application, how much is the question, like, is it we could give these things names, like, is it about spam? Is it a how question? We could give these properties names, right? Is it a humorous question? And when we search, we don't want to return, if someone searches for how to make spam in a humorous tone, we don't want to return this thing that's like, or if this is our query, maybe how to make spam in a humorous tone or something. We kind of want to return something that's as similar as possible, right? We want to return something that's like pretty close. Not this thing up here. So when I think about nearest neighbors, when I say the term nearest neighbors in vector search, this is what I'm really referring to. And it's very, very different kind of problem than what we're used to as search practitioners, which is like, I have an inverted index, something mentions the word spam, which is 1 or 0, maybe an integer counter if we want to take into account term frequency. I match it or I don't, and I return those results. That's what we might call a sparse vector because it has one occurrence of a word out of millions of possible words. Whereas we call these dense vectors because everything tends to be non-zero. And so what we might have is something like, we know this is the question that might get answered. We know that there's a document D that's very similarly related. And all we do when we're building a graph is we're basically mapping all of these similar things together. Any questions so far? Feel free to.
So I guess I have a question. So
Yeah, sure.
I don't know a lot about this, but let's say you said hundreds of dimensions. So how do you kind of weight them to see which ones are most important?
That's a great question. Usually you don't. Usually they're normalized, and usually they don't have any. I gave them meaning here, just as an example. Usually they're statistical in nature, but usually they don't necessarily have meaning. You might weight different kinds of vectors, like if you have a just like search. If I'm searching the title of a document versus the body, maybe you give those different weights, or if, depending on different natures of the snippets that are in that. So those problems still come into play, and things that we've always done in terms of manual relevance tuning or learning to rank can still matter.
What's the representational data structure behind this?
What do you mean by like a?
How are you storing this? Like, is it a multi-dimensional array, or like?
Yeah, it could just be a giant matrix that's like however many data rows, maybe by 300 columns, like a NumPy array. It's very common. Or it could be like row by row. Any other questions? These are great.
Are there any relationships between these, or do you track relationships between 2 points, or?
Usually not. Not in the classic sense. I know a lot of what people want to do. So a lot of what we're used to in search is we have a document as a core entity. A lot of what you want to do, at least in language-based vector retrieval, is really snippet it up and say, like, this document has like these 10 vectors in this body or something. But that tends to be like more about the data itself.
So in that particular case, like if let's say if you have a document and it has 10 vectors, and you want to come up with the nearest neighbor for that document, so would you just like how would you calculate that? Because it's not just one.
Like you have your query, and then you have like 10 snippets, like they might be 10 sentences. There's a couple of things people do, like it's, I believe that's called, the general sense is like, I think that's known as pooling. I could be getting the term wrong, like how you weight those different things or come up. There's ways of coming out with a vector that represents just that document.
Oh, I see.
But then you can also do things like, something that works really well is literally just picking the max, the most similar one.
Oh, I see.
That also works pretty well. Or like some weighted, like 90% of the max plus some percentage of the sum is also a thing people do. Yeah.
Is there any significance to having, or any reason why weights would typically be a negative number to a positive number versus just 0 to 1?
Only because they tend to be normalized to a circle. So you can think about this as like there's a circle, and every vector gets squashed to be something on that circle. So we divide every point by its length. We call that a unit vector. And that helps a lot because it just makes things more efficient when you do like the dot product similarity, which is literally one way of getting the brute force way of getting these together is to just multiply them. If these were normalized, which they're not, because some things are greater than 1, you literally can be like 0.9 times 1 plus 1.1 times 1. If they're not normalized, then you have to do things like, oh, well, I have to divide it by the length and normalize it beforehand. That's called the dot product or the cosine similarity. Yeah?
Could you touch on how models inference the vector, or how models determine the weighting of the vector, the elements in the vector?
Yeah, usually it's often, think someone used a really good metaphor of like, there's an algorithm that works really well for unknotting all headphones. Have you ever gotten your headphones tangled? And apparently the algorithm is you jiggle them. You keep jiggling them, and they eventually get loosened up. And you're sort of like, gradually it gets looser and looser. That's, in a way, a lot of these things are literally like word2vec is literally like, I found a case where this word occurs with this word. Let me pick a random dimension and like jiggle them a little closer together. Or let me find a random dimension. Oh, they don't occur together. There's a negative example. Let me move them apart from each other. It's like, that's, word2vec is something that kind of started this, originally back in the day. And then a lot of these things are much more complicated, like transformer models. We're literally like back propagating weights through a deep neural network. And that gets really deep into how that stuff works, where the meaning of the vector is in some ways more related to an input that stimulates an output. So it's like you have two vectors, and you're classifying whether or not they're like, let's say you have a sentence and you just like get a random set of weights for each sentence. You literally can be like, you have a ground truth that says whether or not they're related. Someone's labeled data. And you're trying to minimize the loss function at the very end of that. So you're trying to maybe turn a 0.5 closer to a 1. And to do that, and to work back through all the math to make that happen, the very bottom are the embeddings of the sentences. And it's really like I said, they get kind of jiggled a little closer through back propagation and calculus that we've all told our teachers we would never apply someday. So that probably needs a deep learning meetup that's from someone much more qualified than I am. These are great. I love the...
Pardon me, is the thing you said earlier, is that something similar to simulated annealing as well?
Oh, maybe.
Okay.
Yeah.
Kind of,
The
yeah.
jiggling?
Yeah. Like it doesn't slow down though, as far as I know. Like it converges, but it doesn't have like an explicit like, okay, our temperature is this or this. As far as I'm aware. Simulated annealing is basically like emulating the cooling of steel. And so you start out with like very aggressive changes, and then slowly over time cool down and make smaller changes. It's used in optimization a lot.
Yeah, they do that for the learning rate in these algorithms, right?
Oh, yeah.
Yeah.
Any other discussion? Great. So yeah, we literally can say these things are related, and I use people here for a reason. Oh, we can create hubs. This is how a lot of these things work. A lot of these vector retrieval solutions work. Literally can create a hub that's like, there is stuff around here that is similar to me in this way. And then you create kind of like express lanes to get there fast. And that's what a skip list is. We're like jumping around, gradually getting closer and closer to where we need to be. When I use the term hub and express lane, I don't know if that sounds like anything, especially for someone in commerce. But to me, it sounds, and that's what hierarchical navigable small worlds is. So if someone says this fancy algorithm, you really can just think about how shipping works. If you think about how people are distributed, there is kind of this national distribution. I've got to find Doug. I've got to find someone in Doug's neighborhood, and I'm going to ship this package. I'm going to get down to the post office, and we can sort of go and collect all of Doug's neighbors because we have it mapped out perfectly. And of course, physical addresses don't change too much in the same way these graphs don't change. You know, this world of data isn't, at least in this, the assumption of HNSW isn't changing too much. So it tends to work. We can map out the space in a very complicated graph kind of structure.
Is this something related to the triangle property? So if I want to go from Ed to Tom, right?
Mhm.
So my understanding so far is that you can't, like, if you want to go from Ed to Tom, instead of calculating all the distances from Ed to all other entities, you know how to get from Ed to the post office, right?
Yeah.
And from the post office knows how to like what the distance to Tom is, I guess.
That's a good point. The tricky thing is when you get to high dimensional space, small differences in the like Ed to post office to Sue can, like, things that seem like they're really similar, like through the transitive property, actually can be very dissimilar because they might be similar in very different ways. So like post office and Sue might be similar in all the ways. It's like I have a friend who likes going to the movies and hates mountain biking, but in all other ways I'm really similar to them. And then I have this other friend who loves mountain biking like I do and then hates going to the movies. That might be like that relationship there. So that makes things interesting when you get to high dimensions, where you assume that like if you map this as like a 2D grid, like, oh yeah, I just walk 0.01 there and I walk 0.04 there. It's not quite as, things get weird in high dimensions. But what you're doing here, you're absolutely right. When you're using this algorithm, you're sort of like zooming in and you're checking to see, you know, the location of these different things, and you're basically traversing a graph. The graph is constructed with different trade-offs for like how many neighbors I'm going to be connected to. I'm either a social hub that's connected to like 500 people, and that's a very expensive life and makes my, lots of stuff going on, or I'm connected to 2 people. And there's trade-offs there, right? If I'm connected to 500 people, then I can connect you to somebody and you can traverse me as a graph. If I'm connected to 2 people, well, you're not going to spend a lot of time searching around at least, but you might not find what you need. Questions? Cool. So real life, so this is how the graph regime we're in now. Real life, it's not particularly easy to update this. There's a lot of stuff around, for example, it's very memory intensive. So all of this assumes this is all entirely based on memory. Persisting and loading from disk. There's actually there's a new challenge called the billion vector challenge, which is much more, you actually have to deal with the disk because you can't deal with a billion vectors without paging stuff or figuring out how to work with disk and merging. So if I collect a lot of data, and this is something that plagues, is an issue in Lucene that the Lucene community is working through. If I collect a lot of data and commit it to a segment alongside the inverted index and all the other statistics, I have a graph there, and it's like a version of the zip code that existed when, 10 years ago. And then all of a sudden new stuff comes in, and it's like all the new houses get built in my neighborhood and all this stuff. And now there's a completely new version of the neighborhood and all the people that live in it. And that gets committed. And so we have 2 graphs that we have to search and traverse. Kind of annoying. You can do that. Might be slow. What happens when you merge them? And if you look at a lot of Lucene stuff right now, there's a lot of problems around stop the world stuff with merging HNSW segments, and creates a lot of headache and heartburn. But it's not just Lucene. A lot of databases have this kind of like structure where you kind of batch collect some data, you persist it to disk. You don't want to maintain this global view of the world just for vector retrieval. You don't want to necessarily treat it like a special snowflake. So yeah, sure.
Sorry. How much of that is just the graph representation versus like vector retrieval, right? Because are there like other like non-graph-based methods that don't suffer from like this merging issue?
I feel like I put you in the talk to like,
All right,
yeah,
all right.
yes, but they come with opposite trade-offs than we're talking about here. Yeah, so just this is just a call out to scan, disk ANN, that are kind of like different takes on HNSW. The HNSW nodes actually like kind of point to disk. So you can imagine at Sue's house, we've somehow mapped all the rooms of Sue's house, and we're like, well, Sue's spouse lives here in this room, and children are there, and we can somehow page them up for disk if we need to. There are a lot of great stuff like that. So what I ask is, are we really solving this problem from first principles? So if our first principle is to win this competition, then maybe we are. But I kind of feel like we're at this point in vector search of a local maximum where people are really just learning this stuff, and this may even be your first time even seeing HNSW and all of these things. And we're starting to master that. And then I think people are also at the same time putting stuff into production and realizing all of these other pain points. And realizing that just because there's a pretty graph that shows speed relative to recall, that doesn't mean things will be easy to operate. So I sort of wonder, are we just continue to put lipstick on a pig? I don't know. And I don't mean to say that HNSW is entirely unworkable, but I think it seems like when you look at what's happening, we're sort of like working to mitigate it, a lot of these things, as opposed to sort of fundamentally rethinking the problem. And maybe that's okay. There are definitely benefits to it, but we have to just be aware of what those are. So, yeah, sure.
I mean, there's a whole class of algorithms based on Microsoft's disk scan, and there's a bunch of papers, various things, and I think scan might be one of them.
Yeah.
I mean, do you have a general opinion on those?
I don't. I wish I knew them better, other than my sense is that they tend to be related to, you might know more about them than I do, honestly.
Oh.
They tend to be, my take on them, and I could be wrong, is they tend to be sort of like graph-based, but in a way that is disk-friendly. Kind of like I said, like the graph is actually pointing at a centroid that then is like all of the stuff on disk that has data, that like a long list of stuff that I can page back from disk. People talk about the curse of dimensionality, like the more dimensions, things get weird. There's kind of a blessing of many data points, where if I have a lot of data and I know that I've found something that is similar to me, there's probably other data points that are in that cluster of stuff that's similar to me, just by the sheer fact that there's more data. And so that centroid in memory graph can stand in for lots of other things that we might actually have on disk somewhere.
Like a sample.
What's that?
Like a sample.
Yeah, exactly. It's kind of like a sample, or a busy city or something. We know that if they live in that building, there's a ton of people living in that building.
Can I ask a
Yeah, sure.
nitpicky question? To what extent is that distinct from like quantization in this? Yeah, sorry, yeah.
Oh yeah, that's great. Like quantization, I think is just a lot of tricks to save memory and like scale. Like obviously, like the most obvious thing being like to go from a floating point to an 8-bit integer, and then there's also different kinds of quantization that like take every fourth dimension, try to cluster them together. That's probably
that's what I like the PV
yeah, exactly.
Quantization, right?
Yeah, exactly. You can sort of like, it's a little bit different. Like it's the same idea. Like there's like a centroid for that for things, but in this case, it's more about like, oh, there is a centroid, but we're pointing at disk because we feel like there is a more or less a super node's not probably a good thing. There's probably a better terminology, but there is a thing. There's a huge grouping of stuff, and we don't need to have all that in memory to be able to find similar stuff.
Got it.
So I'm just a caveman. This vector search world frightens me. So this is caveman vector search. Basically dumb hashing. So you can do stuff like this. We talked before about dot products. Sometimes a dot product, because some of the numbers are greater than 0, that dot product will turn out to be a 0, or greater than 0. Sometimes it'll be less than 0, just because the sum just works out. It's just entirely random. And we can literally do something where we say, well, the things that are probably on one side of this hyperplane are slightly more likely to be similar than the stuff on the other side. And by random hyperplane, I literally mean we draw a if we have 300 dimensions, we just pick a random 300 dimensional vector from that space. We generate all those numbers, and we dot product it with all of our other vectors. Some things are above, some things are below. And if we do this enough, we can come up with basically a hash, because if we have 3 projections here or 1,000 projections, we can do dumb things like, oh, well, all the things above, for each projection, there's going to be a bunch of stuff that's, this vector is either above or below, and if it's above, we'll put a 1. If it's below, we'll append a 0. And of course, we're doing actual bits, not strings here. And probably things that tend to have the same hash will be more similar. And that is true. There's something called the Jordan, and I'm going to not say this right, Lindenstrauss lemma, that talks about where the upper bound of this is, of how doing random projections to make dumb hashes works. And of course, to do the query, we do the same thing. We say, oh, there is a query. We see, and you don't have to worry about this stuff, but we more or less see how many bits do I share with if I hash myself? Yeah.
How many sample slices do you need in order to properly compose a hash compared to a slice of data?
Yeah, so hundreds to thousands.
Okay.
Depends on the volume of data. But we can do the same thing with the query, get that same bit mask. And if 90% of something in our data has the same bits, literally, as what's in our query, they seem to roughly be, you could say they have actually it correlates really strongly with the dot product or cosine similarity. You're basically compressing a way of recovering that. And don't worry about this code. This is just a super optimized way to do that. Pop count just means count the number of bits. And you can go to my blog, and I try to make this as fast as I can. I continue to try to make it as fast as I can. And you can see if the other stuff was up and to the right, this is bottom to the left. Actually, it's a bit of a different, might be different dimensions. But you can see here, oh, maybe we can get 0.6 recall for a couple hundred queries per second. Not so great, right? And this is, as you add more hashes, it gets slower, but the recall gets better. So that's really what that's represented. And these are just different versions of me optimizing this. So this is the HNSW graph regime. It does these things well. I will say, this dumb caveman hashing scheme takes very little RAM. It's very easy to update because you're just literally appending to a list or deleting from a list. And merging it is literally like merging a list. And so it's pretty easy operationally. It just might get you terrible recall. And you might ask the question, well, okay, what does it mean to get terrible recall? Actually, what it means is you're still getting stuff that's similar. It might be like you got the 100th item in the top 10, as opposed to always getting the top 10 right. And is that a good thing or a bad thing? I think it's worth asking ourselves, if if we are building something that is then is like a first pass retrieval thing, that's gonna already get 1,000 results, and we're gonna then re-rank them with some other thing, or apply boost or massage it somehow, maybe it doesn't matter. Yeah.
So what is this recall at anything?
Sorry, at 10.
At 10.
Yeah, usually people, usually people mean at 10 if they,
Cool. Just-
but that's a good call out. I should label my axes better.
Harvey, can you explain recall?
Oh yeah, recall is just more or less like, out of the 10 I got back, or did I get the top 10 out of the top 10 that should come back, what actually came back in the top 10, that proportion. So 60% of what should come back actually came back.
So also like how many false positives or negatives kind of plays into that too.
Yeah, exactly. So it's different than precision, which is like out of my set, what is, yeah. Yeah, so there is a spectrum here from highly parametric, the teeniest structures like graphs, all the way to highly non-parametric. And this is an important thing with vector search. When you're parametric, that means we have a lot of knowledge about the fundamental global structure of the data, which is like a graph. When we're extremely highly non-parametric, we assume nothing. We're literally like picking random vectors, and we could append to this anything, and we wouldn't have to like rebuild the zip code structure of the United States. Yep. So we get to partitioning. So you might say most of the time people are trying to make the highly parametric world a little bit easier to update, work with quantization, other things. And I totally think that's valid. I honestly don't know what the right answer is because I don't think anyone really knows what the right answer is. I think, what about the other way? Can we make the non-parametric world a little bit smarter? And actually, yeah, like why, and we might ask ourselves, why can't we just like do something dumb like this? Just like, oh, just get the index and point at the thing. And this is more or less what the field of space partitioning is. So we can do things like a KD tree. So this is just another kind of partition. Stuff is above, stuff is below. And we pick some random point, except in this case with KD trees, it's always like on an axis. So it's like y is greater than or y is less than. And we can go down one direction or the other. And then we are now working in this little neighborhood. So we're working with a little bit of structure to say like, oh, you know what best splits this is if we put this line here. Usually you pick a line that's based on the median of the data points. So you say like, well, half the stuff is over here and half the stuff is over here, but only in this part of the tree.
What determines what the median of those data points is?
Just literally like, of the stuff that's below this,
Yeah.
the median, would it be, in this case, it would be like the median x axis, which would be like, that's actually like
I see.
this, yeah. So KD trees, yeah, just expanding that out even further down the other path, you can see the other way we chose a different median. These break down actually, unfortunately, at higher dimensions. There's kind of, if you think about 300 dimensions, it turns out that like that is kind of a blob. If you think about the Earth, for example, how much do we think about altitude when we think about like planning out zip code routes? There's sort of a lower intrinsic dimensionality that actually matters. So just constantly picking a random dimension and splitting doesn't add any information. So what we actually do is bring back our friend, the random projection. And the same way we build trees with KD trees, we can build trees from these random projections. So we have some things are, instead of like necessarily one side or the other, we actually use a split point that is based on the average dot product of or median dot product of these things. So it's almost like we create an axis ourselves using the random projections. It's a bit easier to think about on a sphere because these are unit vectors and we're thinking about angles. Some things are within this is our projection. And things that are a dot product with the projection are pretty close to its endpoint. Of course, this is like 300 dimensions. And then there are things that are going to be like past this sort of like split point. And before, when we were doing normal random projections, it was like literally 90 degrees. Some things above, some things below. This is a bit smarter. We're saying like some things this seems like more stuff groups closer, so we're going to make this adjust the split point to be a little bit closer. And literally build a KD tree, similar thing out of this. And you could follow this along. It's the same kind of situation. And we can represent these as a binary hash where it's like, you could see here king. This is king and all its nearest neighbors out of a glove data set. So like word embeddings, all the words that are related to it. All of these things they go down the left path. That's good. And then some things go down the right path where they seem to split off, and some things go down the left path. So this is just following the path of this word as it goes through and gets classified into this random projection tree.
Can I ask you a question?
Yeah, sure.
It's hard for me to look at this and not think of like an SVM. So like, have you like thought about like instead of a random projection, like picking like the vector that sort of maximizes the separation, between? That's
a really good thought. It's funny, I was playing with different variations of this. I was like trying to think about that. The tricky thing is usually with an SVM classifier, some things are like labeled.
What's that?
Some things are like labeled.
I was going to say, yeah, exactly. You're doing, yeah.
But I still have that same thought, like what would be the most efficient split is an interesting question. But of course, when we're just dealing with these like random projections, there's just like a reasonable chance that every time we introduce a projection, we're going to have error. If we follow king and its neighbors, we would like to have them all like clustered at the same leaf in the tree, but they get kind of split off because it just so happens that at these things sort of get sliced off, and we'll talk about that in a second. We get unlucky. We get these like really unlucky splits where it's just like, oh, these things like king is here, and like, I don't know, queen is there or something. And that unluck is pretty common. And you can see it happens like 68% of the time. When we're just building hashes, it doesn't matter because it's not hierarchical. One doesn't depend on the other. And this is kind of like the rabbit hole I started to go down, was similar to what you were thinking, MJ. Can you pick like a good projection? And you can actually, I'll show that in a second. You basically just have cursive dimensionality, 300-dimensional sphere. Some things get lopped off. Random other things get placed in. And it's like, how does this happen? It's completely counterintuitive. Yeah.
I mean, why aren't we thinking about what's not similar, right? The opposite. And just discounting items that are not matching whatever the objective is, instead of trying to find similarity.
I think it turns into the same problem, right? Because you have to, if you're not similar to a query.
It's easier to typically, at least in a human, it's easier to say what they don't like than what they like, or what is opposite of that. How king and queen are not similar, then how they are similar.
It'll be like a gravitational pull in one direction toward the concepts that separate them, right? So like a gender role in that case might be further on the sphere in one direction.
But I think you get into like a multi-stage process, right? And so if you can eliminate noise, the algorithm's performance change?
I think I would ask, how do you get rid of things that are not similar? Because I think that just turns into a nearest neighbor's problem for the opposite of what you're searching for.
So
Yeah.
maybe it like would help to like mention like what the brute force approach is, and then like how this like sort of
Yeah.
simplifies the brute force approach. Like where like the brute force is to calculate pairwise similarity or dissimilarity between everything, right?
Mhm.
You know, whereas this is sort of like trying to figure out like, well, I'm just going to cut it off here, and like everybody above the line, you know, is here, and everybody below the line is there. And I think that like in that context, it's probably the same, right? Similar, like, or dissimilar, right?
Yeah, because you're sort of like, I'm actually trying to do that. I'm trying to be like, oh, there's all this stuff here I want to cut off.
Exactly. Yeah.
But the problem is, this is like what we'll see. This is just one, like this flat circle is one of 300 dimensions. Even a random projection, it's like an arrow pointing in 3 dimensions is still 1 dimension. And you can think about this as like the zero, like if we reorient, you can reorient a vector space to be like, oh, this is, this R is our random projection, R dot king, R dot queen. You still have 299 degrees of freedom at every split level for something to go wrong. It's literally, it's similar to, it's basically the same as like, I have a friend who likes mountain biking, I like mountain biking, but it turns out we completely hate each other's guts because we, I don't know, some, you know, different political views or different something or different this, everything else is different. We can't stand each other. It's like my mountain biking competitors. I actually don't do mountain biking. I don't know why I can't. So don't enter me in any competitions.
Broader question.
Yeah.
Has this problem, I guess vector search, whatever term, fill in the blank, right? Has it been solved, or is this our best attempt or guess at how to do it well?
Oh, I think we're totally best attempt to guess to do it well. Whereas I think you could say like term-based retrieval has been solved, but people still make improvements. I think this is still a wide open space,
Okay.
exactly for the reasons I talk about, because yes, we've maybe solved the problem of doing well in ANN benchmarks.
Mm-hmm.
But I think the problem of building production systems that can be updated and scaled and easy to turn on, we don't even think about what these data structures are on,
Right.
is definitely not solved. Yeah, so these are neighbors, right? But you could like literally just pick 2 things and you see how different these people are. We can improve split efficiency, but it doesn't help that. You can actually do a PCA. And this is just, a PCA just says like what direction does the blob go stretch the farthest. And in 3 dimensions, you might be like, oh, well, obviously I want to cut the front of the football from the back of the football. It helps a little bit. You can also just have a ton of forests. So, and this is what an random projection forest is. And this is what, this is, you can see, I was like, I felt like my code was broken until I saw this graph. And I see one tree, and the error is pretty phenomenal, just with one tree. And this is what Annoy does. So Annoy, talked about Annoy before. Annoy is a sort of an OG, nearest neighbors solution. Severe delta in performance for the same recall to HNSW, like this is ANN benchmarks. And yeah, you can see these are just different data sets. Annoy kind of like as you get more complicated data sets, the performance and recall kind of falls back. Whereas HNSW tends to be a bit closer together and it's faster. And then, of course, but like we were saying before, the build time, and this is literally like letting a machine build this without being interrupted by other things that search engines are always interrupted by. Annoy you can build relatively quickly. HNSW with phase takes 60 to 100 minutes. And then we don't even know about stability, update times, all that stuff, right? All the complexities we talked about. So I haven't reached a conclusion. because like you said, this is an open space. There are trade-offs. I think we're at a place where we have to think about what the right solution is. Something that's really coarse grain or for something really fine grain. And I think I've talked about these quite a lot. Highly parametric, really just like fine-tuned to the geography of our vector space. Literally, we fix the cursor dimensionality by mapping it, right? And we hope it doesn't change too much. We hope our maps don't go out of date. We pre-compute the right answer. But of course, like our maps go out of date and we have to like rebuild our maps and hire more cartographers. Whereas like highly non-parametric, that's like, I don't know, being out in the woods with a compass or something, right? You're like maybe, and you know generally how to track animals. But we can like maintain these. It's not gonna require a lot of sophistication to deal with all of the updates and churn that we have to deal with.
So the algorithms that exist, right, that we saw on the ANA or the
ANN benchmarks?
Yes, yeah,
Mhm.
the benchmark. So where on the spectrum, what percentage fall in the highly
Parametric.
highly non-parametric?
Oh, I would-
Or can you do a hybrid too, or?
Oh, yeah, I think a hybrid is totally doable. I don't think, and there may be things on there that do a hybrid. For the most part, it tends to be very highly parametric.
I see. Okay.
And then people will do things like quantization and stuff to like improve some of the downsides. Because like that benchmark's just built, I mean, they say this, it's built to be in memory, it's built to build up front and then search. And so it's just like, if you're, I don't know, if you're a competitor, you're gonna focus on that, on optimizing that. But I do think it's important to think of other benchmarks, other ways of measuring this, have other competitions, because that's just one point of view.
So highly non-parametric, you compute everything in real time, every single time? Is that?
Highly non-parametric, you just don't have a map of what the vector space should look like.
Okay.
You don't know that if I want to get close to Willis Tower, I go this way and that way, and I'm there.
Tower, come on, man.
Willis? Sears Tower. Oh, I'm sorry.
Chicago.
So the idea is in real time you would build that vector map is what I'm hearing then, or no? Space or?
In non-parametric, you sort of have a very coarse grain, like a sonar system.
Okay, I see.
You could think about it that way. Like literally you're like probing the space as you're walking through it.
Right, and hope you get lucky with what you get.
Yeah, the metaphor kind of breaks down with maps and things. But yeah.
Okay, so what percentage of algorithms, like would you say 90% fall in the parametric?
Oh yeah, definitely.
And what's the frequency at which, obsolescence is detected and then the vector maps are recomputed or rebuilt?
That's a great question. In a production system, like
Yeah.
when ANN benchmarks, they're like pre-canned data sets,
Mm-hmm.
so that doesn't matter.
Right.
In real life, like just the same as the update rate of any search system. If you have an embedding for every sentence of your whatever, then every title, then every time that's updated, you're going to have to like redraw the map, so to speak. And hopefully, it's generally the same, so it's kind of like things kind of bucket together still, but just like how vocabulary shifts over time, like in an inverted index, the same thing can happen with embeddings.
Is a key tenet of parametric algorithms eventual consistency or no? Or is it always like going to give you the right value?
That's a great question. I haven't thought about like consistency and cap along those lines. Usually most search is just eventually consistent.
Sure.
I have a question around
Yeah, sure.
anecdotes on like these non-parametric approaches versus relevancy.
Mhm.
Like, for like basically relying on the vector searches like first pass, candidate retrieval, and like having second pass or other ranking layers. Like, does maybe stacking like different non-parametric approaches like work in
That's a great
practice
question.
as like just enough to augment like lexical matching?
Yeah, there's other kinds of hashing that I haven't talked about. There's, so random projections is the simplest. There's something called spectral hashing, which uses actually like, well, I won't pull it up, but that basically like does some principal component analysis and kind of breaks apart the space that way to be like, oh, these are the actual dimensions of the space. And then there's using a deep learning encoder decoder to build like a layer in between of a hash, and you can use that as well. So I think, yes, I think that I haven't played with that. I do wonder if you like had an ensemble of hashes, how well that worked. Those different things, like having the PCA of the data and the doing an encoder decoder kind of thing, are slightly parametric because you are like training all the data and you're kind of like seeing patterns, and the PCA of the data is like literally like, what is the football blob shape of this? And that could evolve over time, but it's not nearly as parametric as drawing a graph and mapping out the entire space. Yeah, so fine grain retrieval, coarse grain retrieval. I think we've talked about this. I think they have trade-offs. One for I want to gather 1,000 candidates. The other one, like literally, I need the top 10 to be right in my vector search. Whereas obviously the top 10 can still be right on the right if you're dealing with a solution that's very, very much focused on other things. And I sort of wonder if I don't know, if my perspective is a lot of applications are switching more and more to be basically retrieval driven. They look more and more like search. Like recommendations could be driven by a vector database. Obviously we have things like RAG. Search has always been in this kind of space of quote unquote real-time retrieval, or more real-time than batch
I've seen
recomputing.
RAG a lot lately on LinkedIn. What is it?
We have a RAG expert. Her name is MJ. No, it's basically, it's just, so you know how you type in, I say, what's the best gift for a 4-year-old? And something goes back to maybe a search engine, like gives context for all the things I've talked about in the past, or maybe like my database of, this sounds terrible, but like a 4-year-old I've like talked about like my son or something, I don't know. And it says, oh, you're talking about so-and-so. It like literally makes the prompt filled in from a search system or something like that. And then it can give you, oh, you're talking about, little Timmy and they like bikes or something. You should go get them that gift.
It stands for Retrieval Augmented Generation.
Yep,
Yeah.
retrieval augmented generation.
Is that another algorithm or what?
It's just a means of going and injecting stuff into ChatGPT.
Only if you want VC funding, then yes,
Right. You're RAG enabled.
that's right.
That's
Or
right.
centric rather than
And people are getting into the space, and they're like realizing all of the things search people have realized for a long time. There's like, oh, I can't just dump random stuff into this. I have to care about the precision of the results, and I might have to re-rank it, and like all these, recency might matter. It's like,
But it still depends on an LLM, right? There's an external.
it's both. Yeah, it's
So the first part is a vector search, but then the second part is you're still relying on an LLM and its internals to give you the right answer.
yep,
So it's
absolutely. And it could be
there's a dependency there.
And it could be a fine-tuned LLM, like to your use case, or it could just be off-the-shelf ChatGPT or whatever. So, I swear this is the last slide. No, it's not. There's this famous debate in physics where Newton and Leibniz disagreed on the nature of space. Leibniz thought space was relational, that things only had meaning in their relation to other things, which makes me think of the graphs-based approach to vector search. And Newton was like, no, there X, Y, and Z have absolute meaning, and there is a thing called space in the void between me here and there. And this was like a long philosophical debate I once watched a YouTube video on, and therefore I'm an expert now. And this reminds me of like the space partitioning view of the world, highly non-parametric. So
Yeah, I guess that's what I was asking, right? The relationships, okay.
yeah, exactly.
So basically today's vector search takes Newton's philosophical approach as opposed to Leibniz.
No, I would say the opposite. It takes
Okay.
Leibniz. So it takes maps the entire relationship of everything to everything.
But not to itself. Not in its own XY.
Right, yeah.
Right, okay.
And I just threw a random slide of other thought-provoking, interesting talks that often have nothing to do with search or vectors that you might want to check out, just that I watched in the last month. So, cool. Thank you, everyone. Yeah.
Can you talk about some of the problems Lucene is actively solving in this space and like what some of the limitations might be just based on the existing Lucene architecture?
The limitations are a lot of the stuff around that would probably exist in a lot of data stores, which is just the segment-based view of the world, which I feel like it's a common kind of way that more or less NoSQL kinds of databases have come up, where it's like, we get a lot of data, it's eventually consistent, we write it to disk. We get another 1,000 documents, we write it to disk. And just, merging, if we have an HNSW graph, merging these graphs it's like you're getting two cartographers to agree on what the right map is. And you have to sit there and reconcile these two graphs, and that's a non-merging HNSW graphs. And I don't know as much about this as I wish, there's people in Lucene who know way more about these problems, but this is kind of reputationally the problem. And I suspect other databases will have it. And I suspect things that were built with vectors from the ground up and maybe focused on something like HNSW from the ground up won't have that problem. But they may have other problems that I don't know if we've encountered yet.
As a follow-up, are you seeing like a tension between like CPU and GPU like available? Or is that
the
not really relevant?
The GPU side is interesting. I haven't seen that as much in vector retrieval. I think NVIDIA has a thing they're pushing to try to make us buy more NVIDIA chips, which, but it's, I can't remember the name of it. Someone DM'd me once with a link to something. But yeah, everything I've seen has been basically like normal CPU-based kinds of things.
Sorry, I don't know what Lucene is.
Oh, yeah, it's just, do you know Elasticsearch?
Yeah.
So it's the Java library underneath Elasticsearch.
Oh, I see.
Yeah, so the history of the project is since late 90s, there's been a Java project called Lucene, and it's got all the low-level crazy details, and it really pushes the limits of what Java can do. I can't remember if it was, so the creator, Doug Cutting, he either knew about search engines and wanted to learn Java, or knew Java and wanted to learn search engines. What are the other? And so it's now it's Java. It's a search engine built in Java, for better or for worse, and so it really pushes the limits of what Java can do performance-wise.
So when you build search systems, what language do you use?
I use, there's often, you can think about it as like there's a database. There's like Elasticsearch, there's Solr, there's OpenSearch, there's a vector database. The language could be anything. It could be like top 10 programming language. There's client libraries for, just like when you write a database application that talks to MySQL. At Reddit, we do a lot of Python and Go, but it could be a lot of things.
So is that just the client libraries or the search engines themselves?
So the search engines themselves, the Lucene ones will be Java-based, and you can go under the hood and write plugins to do low-level things. Makes it really extensible. So yeah, you can use a Java or JVM language. Yeah.
Oh, sorry, go ahead. Oh, I was just gonna ask, like, what are some of the unsolved problems that you have at Reddit that you're able to talk about that you're starting to use vectors for?
I don't know, John. What are some of the
I don't know, Doug, what do you think?
I don't know. I feel like, are we still recording?
We can stop. I'll let it
No, it's, I don't know. I think I could just say that, like, obviously search at Reddit is very important to us. It's very important to me. And I feel like Reddit has a lot of rich natural language and lots of things that would benefit from vector search. So I don't know how much I can say about anything, but you can use your imagination for that.
I think maybe one way of putting it is people think of Reddit as one thing. It's not. It's like millions of different communities talking about different things in different ways. And every single one of those communities, that's taking it too far. You cluster those communities together that have specific kinds of behaviors and specific kinds of discussions, and being able to deliver a really good result for, finding stuff on Am I the Asshole is different than finding results for, our science. Like they're different things. So I think that, that's probably the biggest challenge I see, at least, is it's not just one thing talking about things the same way.
Yeah, I think about Reddit as like the long tail of the long tail too, because it's like people come to Reddit, they really want everything from like, there was this niche product I use in this field, I want to see other people's experiences because there's nothing online that's professionally reviewed anywhere, to people just having like, mental health issues and wanting to see what other people's experiences are and connect with other people. It runs the gamut, but there's a strong sense of like social connection and that kind of thing.
Or just finding people who have put a 69 in their thing so you can respond with nice.
Exactly.
Which is big Reddit behavior.
Exactly.
Yeah. Well, how many people actually use the search box on Reddit versus just search for their thing on Google and say Reddit?
Oh, far more of the latter, I would say. Will hopefully one day will help with that a little bit. But I think a lot of people go to Google and type something Reddit.
It's not just
That's the
Reddit.
only way Google's useful anymore.
Yeah.
The vector search techniques that you were talking about, do they work only for natural language, or let's say if I want to search a mathematical structure or an equation formula, does it work for that?
Good question. If you can find a way of expressing that as a dense vector, then you could do that. So there's natural language, but most common things that are turned into, there's like open models. I don't know to what extent open source, but there are publicly available models out there. There's like images. There's images like there's clip, which is image to captioning. All kinds of things that like there's audio. There's many kinds of media that people have trained models and turned them
So
into.
for each of these domains, you have to have a way of translating the query or translating the knowledge into a vector.
Mm-hmm.
And so that is domain specific.
Yeah, you not only need a way of translating that knowledge to a vector, you have to have a sense, you have to have constructed them somehow. And so let's say we make a set of vectors based on songs, and we want to group together similar songs. And the first thing, I have to think of a vector that's actually more analogous to a search index, even though we don't think of it that way. Because in search, how we would think about that is, I want to find similar songs. Well, let me extract all the metadata about the songs and like the artists and all this stuff to put it into a search index. Except with a vector embeddings, it's like, let me statistically define what it means for two songs to be similar. And then just like let the wires jiggle until the numbers get close enough for my definition of similarity. You're still over here defining what similar means. It's just maybe all ahead of time and whatnot of like, what does it mean for two songs to be similar? No one has like solved that problem because it's fundamentally specific to whatever relevance or search problem you're solving. You have to define what similar means to you and then find a way to hire smart deep learning people to jiggle the numbers together until it comes close to that. Yeah.
Doug, what have you seen just in terms of production adoption? I mean, either Reddit or Shopify, any publicly referenceable, like, big production adoption stories for vector search? Can you say publicly, is Reddit using vector search?
I'll edit this out.
I mean, I don't think it matters. We would love to, but yeah, it's something that's sort of in progress.
Yeah.
And then I don't know. I'll let MJ speak for Shopify. I don't know what's publicly available or not, but yeah, I don't.
Yeah, I mean, I think we can definitely say like we're using vector search for like our shop app.
Yeah.
Yeah, that's definitely.
Yeah, there is a really cool. If you go to shop.ai, is that it? I think it's shop.ai. There's a really cool thing that a sibling team to the team MJ and I worked on, which is like helped to build this, which is powered by a search that I worked on like 4 versions ago. But I want to find a gift for a friend's dog that is allergic to peanut butter. Tell me.
And then we'll like show, see.
Yeah.
And there's no call to OpenAI involved?
Well, so the vector search part is definitely like just regular vector search, but then there's also an LLM doing like the chat.
Yeah.
But like you can see that like it's like allergic to peanut butter, and then first result is like hypoallergenic dog treats.
Yeah.
So which part's happening first? Is it the filtering of allergic to peanut butter, or you're finding all the things and then you're filtering out? You know what I'm saying?
Yeah. So I mean, well, that's like a different topic, which is sort of like how filters and like vector search interact, because like I don't think, Doug, you really like. I mean, that's like its own can of worms.
Sure.
But I would say that in this case, they're happening kind of simultaneously, and then we're also using that information to, help provide context to the LLM.
Yeah.
Is this Shopify data?
Yeah, this is Shopify.
So this is there's the Shop app, which is an app you can use to search all the Shopify merchants. And then this is sort of like a web version of an interface that just demos the chat functionality.
Scott, to go back to your question, I did read an interesting article that Amazon Music is using billion scale vector search, and that's like their broad search use case. I haven't found a lot of examples of people actually like using it for realsies, but I thought that was an interesting read. If you want to, I can send you the link if you're interested.
I definitely would, if you want like concrete content, like Haystack tends to have fairly concrete. Haystack is there's Haystack, the question answer. Haystack means like 20 things, but one version of Haystack is a conference for search relevance, and there's probably stuff in here that has great concrete vector search use cases, and you could reach out to these people and talk to them.
Everyone I know using it isn't using it necessarily for every search. They're classifying or
yeah, totally.
On no results pages.
Yep, that makes a lot of sense.
Work with a client, and 50% of their searches are one-term product IDs, and they're like, we need to do vector search. Sure we can, but...
You have a vector dimension 1 that's a product ID.
It's an easy one. But there are a lot of nuances to their data that can be, as the long tail pulls out, but I don't think everyone's doing every search vector search.
Yeah, what I see is, and this is always the case, of things you see talked about at conferences is only one small percentage of the actual world, because there's still the 80 to 90% of like, oh, we're still doing like whatever relevant stuff we did 10 years ago, and we're doing one. It's all getting kind of layered together, and just solving different pieces of the puzzle.
Where like real-time updates is like a project that they do for a year and then
Yeah.
they abandon it. So that
Yeah.
they go back to like a batch build overnight because it's one supplier, they blah, 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 and 10 minutes later, you're right back where you started.
Yeah, exactly.
So Doug, let's say you have somebody who's an e-commerce website, they've got keyword search down, and some their boss is saying, we need the vector search. Give me the AI. What do you point to? What do you say to somebody who's like already started there but wants to do this, or at least put their toes in the water?
Like they're chugging along on a search project, and someone from on high says, "Make the AI happen."
Yeah.
Make the AI happen.
Yeah. That is a great question, and through 10 years of consulting, I wish I had an easy answer to that. I think, quite honestly, you make the AI happen, or you choose another, job relationship, or whatever. So
Switch teams.
and you just, it's something that's just unfortunately part of life, especially at sometimes tech companies. Yeah.
But realistically, you're probably going to mix the two.
Realistically, yeah.
Hybrid system. Do you have any kind of experience in mixing the two? Is it just a simple mix that people use?
There's some
hybrid system, or is it more? Are there more structures?
Yeah, there's something people tend to use called reciprocal rank fusion. And it's like Elasticsearch has a document, but it's basically like you score things based on their rank in each list. It's like you score things as if you have two lists, one is from your search engine, one's from your vector database. You literally do like 1 over, your final score is 1 over the rank of this one plus 1 over the rank of this one. So basically, if two things come up as 1, then that's a 2. That's pretty amazing. If it's like 10 here and 1 here, that's a 1.1. If it's half up here and 1 here, that's a 1, it's 1 over, so it's like a 1 plus 1 over 5. It's a little bit better. And you want, it's basically like telling two groups of people to brainstorm ideas, and then you're like, the 3 here are the same as the 3 here. That sounds like a great plan. Let's do that. Yeah.
Yeah, going back to Joel's question about making the AI happen. Just
do you have a plan?
Open AI, the work that they've done. I mean, you could either spend a fortune building your own models.
Oh yeah, totally.
For AI, or just leverage what a lot of companies are doing that. Bing.
Absolutely.
A lot of companies are just incorporating open AI with their products and charging you for it.
Yeah, totally.
Or you go directly with open AI. So if you want to make the AI happen, just pay developers to leverage open AI. And leverage that with your product. Or create your own, go through the trouble of training your own AI models, which is a long and rigorous process.
The question I always ask them back is, clearly articulate what is the problem you're trying to solve.
Yeah.
Right? A generic statement like make AI happen because you attended a conference and heard the buzzword. It's not very practical or fruitful, especially when you have to justify the investment later on to your leaders, right, or whichever leader is saying you have some accountability reporting up to, right? So they need to be able to articulate what value did that add for the product or the business. Or
you know what my number one piece of advice is in these situations? It's like the weather in Scotland. If you don't like the weather, wait 15 minutes. If you wait 3 months and the storm, whatever thing will blow over, and
the next hot item or the priority.
Yeah, or they'll go focus on something else.
The kind of people who say make the AI happen are not usually the kind of people who spend a lot of time worrying about it when it doesn't.
True.
Yeah.
But they have to look good They have to meet some checkbox that's been flowed down to them is the problem.
Also, there's like a pretty good consulting engagement and just like, should I make the AI happen? But like, you know, an interesting question is, should I make the AI?
Right,
You know, what are the practical applications that may be emergent that I could be using? And if not, save me $900,000 in like going down the rabbit hole.
There's usually a problem underneath the presumed solution that is useful to get to, or like some underlying emotion too. That's the other thing. Like I would frequently run into this, not AI, but like when I did consulting, we want the machine learning solution out of the box. We need machine learning in our search. It's like, you need machine learning in your search. You know, and you talk about basic things and whatnot, and it's like, oh yeah, we don't even know, what's an A/B test? Like, how do we even?
What's a judgment set?
Yeah, exactly. What are these basic things? And then it's like, then you realize like, okay, well, I don't know. 95% of machine learning is all this stuff you prepare to get to it, right? So it's like, whether that last 5% is import sklearn and train a model or not, does it really matter? Yeah.
Do you have an idea of, I mean, one of the use cases for vector search is to beat the out of vocabulary,
yeah, totally.
The semantic search, the bridge to words that have nothing to do with each other actually do mean the same thing, which cannot be gotten by solver search or Elasticsearch. So that's one use case, but I think it's, I don't know if it's about 30% plus, minus, you know, depending on the use case. But is there something else now that's more like cherry or, you know, what are the kind of the application?
Well, definitely a vocabulary problem, but just different use cases. Like my mental model recommender system has always been, we pre-compute your recommendations and then we serve them to you tomorrow. And that happens every day. We looked at past whatever and we serve you your recommendations. Instead, I could pre-compute or maintain in a vector database a vector for you and next to the vector of products, and like they just get tweaked every day or even in real time, or the vector of you could just be in a session somewhere. And it's like, oh, well, now you're getting slightly different products because you clicked on this thing. And it's like much more of a real-time thing that in some ways looks more like what search people have been used to for years. But I think like a lot of things are moving to this view. When I retrieve a set of things from the back end, it's not necessarily relating to a MySQL query or whatever. It's like some vector of you that is going to some retrieval thing, and for personalization or for search or for type ahead or for the next word you're going to type, it's all, everything is moving to this, like, I feel like this retrieval centric world that we're going to be living in not too long. Yeah.
We have one more time for one more question.
Yeah. Oh, that's fine.
No, so you go ahead.
Oh, well, so I was gonna ask, like, are you seeing like I know that like getting back to Reddit, like Reddit is pretty text heavy, but are you like seeing like a use case for like multimodal embeddings or anything like that?
Oh, totally, yeah. Because there's, I mean, people post images, people post videos with like very little description, or like, you know, memes. Are like, could you create a whole vector? There probably is somewhere like a vector space of memes.
Probably, I'm sure.
So absolute 100%.
The caveman approach to action memes.
Absolutely, yeah. There's a vector of that screenshot somewhere.
All right, well, thank you, everybody.
Thank you, everyone.
Thank you for joining.